Say I want to build something out of wood. I'm just going to make it two-dimensional rather than three-dimensional just to keep it short. Let's say that I cut a piece of wood, and that piece of wood is constant density, right? The density is the same throughout. Just as a reminder, density is mass per unit volume, which is the Greek letter rho, and it's mass over volume. Or if we were just in two dimensions, we could talk about a two-dimensional density or mass per unit area, or one-dimensional density, mass per unit length in one dimension. But anyway, so there's our density. And let's just say we cut it out, and it's got dimensions of centimeters by 20 centimeters. I'm going to build something. So I don't know what I'm building. You can imagine. Maybe we'll make it up. I'm going to cut out another piece of wood. Let's say that's 10 centimeters square. I'm now going to put these two pieces of wood together. This. And, I don't know, tell me what it is. A chair? It's a two-dimensional chair? I don't know. Anyway, what is the center of mass of this object? What's the center of mass of this object? Outlined it in highlighter. And maybe you can imagine. Let's just try to jump forward real quick and say, the center of mass, because this is constant density, the center of mass of the big piece of wood is at its center. And the center of mass of the small piece of wood is at its center. So we've got this here and this here. So now you think of those 2 points and you say, all right, so the center of mass, so the little piece of wood, this little guy here, pulls the center of mass of this a little bit over there and up a little bit like that, right? So it's over and up a little bit. So maybe the center of mass is somewhere around here. That's not easy to read. Come on. Okay. So it pulls it to the left a little bit and up a little bit. So maybe the center of mass is about there. Okay, let's see where the center of mass is. So what we can do is, even though this is now an extended object, we can still talk about the center mass in the x direction, x center mass. There are two masses here. We can talk about this one mass. Its position is its own center of mass. And this one mass, its position is its own center of mass. So in the x direction, x center of mass is going to be m1 x1 plus m2 x2 over m1 plus m2. I forgot to give you an actual number for density. Let me give you a number for the density. Let's just say that the density is, let's just say it's an areal density. Areal density, in other words, we're just doing two dimensions here. Rho is mass per unit area, mass per unit area. And let's just say that the mass per unit area is, I gotta make something up. Totally made up a number, 3.2 kilograms per meter squared. Okay, don't worry about that right now. But, so x center mass is that. That's going to tell us the center of mass in the x direction. And then we've got a y center of mass because it's two-dimensional. Y center of mass, didn't mean to change the color, but I'm not going to change that now. M1 y1 plus M2 y2 over M1 plus M2. Okay, so in order to solve this, first thing we got to do is define our coordinate axes. Define our coordinate axes. Now, you say, where do I put my coordinate axis? You put wherever you want. Put your origin wherever you want. I don't know. We might choose to put the origin at the origin of one of the objects. It makes our math a little easier. You might choose, I don't know, you might choose to put my origin here. My origin is here. Or, again, different coordinate axis. Maybe I choose to put my origin here. It doesn't matter. Put it wherever you want, but make sure you pay attention to where you put it and where the relative centers of mass are, or relative positions are. Really doesn't matter which origin I use. But I guess I'm just going to use the red one. I'm going to use the red one. It doesn't matter. But let's go ahead and call the red my x and y axis. So this is plus x. This is plus y. Plus y. And so we just got to define our origin one way or another. Doesn't matter. Again, put your origin at the corner of one of the objects, put your origin at the center of mass of one of the objects, doesn't matter. If I put it at the center of mass of one of the objects, it does allow me to put a 0 in the formula somewhere. So that does make things slightly easier, but not a lot easier. Okay, so let's go ahead and, according to the red origin, what is the position of center of mass of 1? Oh, which one's 1? Let's call this is 1 and this is 2. This is 1 and this is 2. So there was a stray mark in 2. To the red origin, the position of 1 in the x direction is 0, right? The position of 2 in the x direction is what? You got to figure this out. The center, the distance from here to here, is 25 centimeters because of the size that I cut the block. The distance from here to here is 10 centimeters because of the size that I cut the big block. And the distance from here to here is 5 centimeters. I don't know. I'm just writing down some distances here. And so from that, you should be able to tell that x2 is to the left of the origin by 20 centimeters, minus 20 centimeters. Figure that out for yourself. The position in the horizontal direction on the x-axis, this position here is minus 20 centimeters from the red origin. y1, y2, I'm going to write them on the same page. Let's just write them over here. y1, the position of the big block is still at the origin. It's at y equals 0, and the position of the smaller block, figure it out, it is 10 plus 5, it's 15 centimeters, plus 15 centimeters above the origin. Okay, so that gives me their positions. Again, I'm trying to find the center of mass of the thing that's highlighted in green. And then, I don't know their masses, but I do know their densities and their sizes. So I need to now find the mass of each object by itself. So the small object, m2, it's equal to its density times its area, because density in this case is mass per unit area. So it's 3.2 kilogram per meter squared times its area, which is 10 centimeters times 10 centimeters, which gives us 100 square centimeters, 3.2 kilograms per meter squared times 100 square centimeters. This is a unit conversion issue now, where on the first exam, a lot of you did not quite get it right. You got to convert centimeter squared to meter squared. So I'm going to go ahead and do that. So I have to convert 1 meter to a centimeter, and then because the centimeter squared, I have to convert the centimeters to meters twice because it's centimeters squared. So this centimeter cancels with the first one, and this centimeter cancels with the second one. So what we're left with is 3.2 kilograms per meter squared times the 100 centimeters squared divided by times 1 meter times 1 meter over 100 times 100. That's what we're left with when we cancel those centimeters squared. And so what we have is 3.2 kilograms divided by 100. So it's 0.032 kilograms, or 32 grams. If it is kilograms, I'm just writing it as 32 grams in case you like that. Do the same thing for the mass of M1. It's its density times its area, because it's our areal density. 3.2 kilograms per meter squared times the area of M1, which is that, 20 times 50, and we can do the math. Multiplying 20 times 50, you get 1,000 square centimeters, and doing the unit conversion, 1 meter over 100 centimeters squared in order to cancel the centimeters squared, and we get 0.32 kilograms, or 320 grams. You might have recognized, if you were paying attention, that the area of 1 is 1,000 square centimeters, and the area of 2 is 100 square centimeters. So 1 is 10 times the other in size, so it's going to be 10 times the other in mass, since we're talking about area here, areal density. Okay, so that makes sense, 32 grams or 320 grams. So let's go ahead and plug those numbers in to the x center of mass, the y center of mass. We get is in the x direction is minus 1.8 centimeters, and the y direction plus 1.36 centimeters. That's the center of mass of the system relative to the origin. Let's go back to our picture. Let's draw a new one. Center of mass is 1.8 centimeters to the left of the origin and 1.36 centimeters up from the origin. So it's actually really super close to the origin, but the new center of mass, the center of mass of the system, is about there. That's the center of mass of the system. In the scale of things, it's not too far off from the origin of the original. Okay, the last thing I want to do, the last example I want to do with center of mass before we move on, is a center of mass of something that doesn't have a constant, that doesn't have an obvious where is the geometrical center versus center of mass. We'll do that next time.